A t-test is any statistical hypothesis test in which the test statistic follows a student's t-distribution if the null hypothesis is supported. It can be used to determine if two sets of data are significantly different from each other, and is most commonly applied when the test statistic would follow a normal distribution if the value of a scaling term in the test statistic were known. When the scaling term is unknown and is replaced by an estimate based on the data, the test statistic follows a student's t-distribution. History: the t-statistic was introduced in 1908 by William Seeley Gossett, a chemist working for the Guinness Brewery in Dublin, Ireland. Gossett had been hired due to Claude Guinness's policy of recruiting the best graduates from Oxford and Cambridge to apply biochemistry and statistics to Guinness's industrial processes. Gossett devised the t-test as a cheap way to monitor the quality of stout. The student's t-test work was submitted to and accepted in the journal Biometrica, the journal that Carl Pearson had co-founded and of which he was the editor-in-chief. The article was published in 1908. Company policy at Guinness forbade its chemists from publishing their findings, so Gossett published his mathematical work under the pseudonym Student. Guinness had a policy of allowing technical staff leave for study, which Gossett used during the first two terms of the 1906–1907 academic year in Professor Carl Pearson's biometric laboratory at University College London. Gossett's identity was then known to fellow statisticians and to the editor-in-chief Carl Pearson. It is not clear how much of the work Gossett performed while he was at Guinness and how much was done when he was on study leave at University College London. Uses: among the most frequently used t-tests are, a one-sample location test of whether the mean of a population has a value specified in a null hypothesis. A two-sample location test of the null hypothesis that the means of two populations are equal. All such tests are usually called student's t-tests, though strictly speaking that name should only be used if the variances of the two populations are also assumed to be equal. The form of the test used when this assumption is dropped is sometimes called Welch's t-test. These tests are often referred to as unpaired, or independent samples t-tests, as they are typically applied when the statistical units underlying the two samples being compared are non-overlapping. A test of the null hypothesis that the difference between two responses measured on the same statistical unit has a mean value of 0. For example, suppose we measure the size of a cancer patient's tumor before and after a treatment. If the treatment is effective, we expect the tumor size for many of the patients to be smaller following the treatment. This is often referred to as the paired, or repeated measures t-test, see paired difference test. A test of whether the slope of a regression line differs significantly from 0. Assumptions: most t-test statistics have the form t equals zs, where z and s are functions of the data. Typically, z is designed to be sensitive to the alternative hypothesis, whereas s is a scaling parameter that allows the distribution of t to be determined. As an example, in the one-sample t-test t equals, where is the sample mean of the data, is the sample size, and is the sample standard deviation. Is the population standard deviation of the data. The assumptions underlying a t-test are that z follows a standard normal distribution under the null hypothesis, S2 follows AI2 distribution with p degrees of freedom under the null hypothesis, where p is a positive constant, z and s are independent. In a specific type of t-test, these conditions are consequences of the population being studied, and of the way in which the data are sampled. For example, in the t-test comparing the means of two independent samples, the following assumptions should be met. Each of the two populations being compared should follow a normal distribution. This can be tested using a normality test, such as the Shapiro-Urowolk or Kolmogorov-Urosmanov test, or it can be assessed graphically using a normal quantile plot. If using students' original definition of the t-test, the two populations being compared should have the same variance. If the sample sizes in the two groups being compared are equal, students' original t-test is highly robust to the presence of unequal variances. Welch's t-test is insensitive to equality of the variances regardless of whether the sample sizes are similar. The data used to carry out the test should be sampled independently from the two populations being compared. This is in general not testable from the data, but if the data are known to be dependently sampled, then the classical t-tests discussed here may give misleading results. Impaired and paired two-sampled t-tests. Two-sampled t-tests for a difference in mean involve independent samples, paired samples and overlapping samples. Paired t-tests are a form of blocking, and have greater power than unpaired tests when the paired units are similar with respect to noise factors that are independent of membership in the two groups being compared. In a different context, paired t-tests can be used to reduce the effects of confounding factors in an observational study. Independent samples. The independent samples t-test is used when two separate sets of independent and identically distributed samples are obtained, one from each of the two populations being compared. For example, suppose we are evaluating the effect of a medical treatment, and we enroll 100 subjects into our study, then randomly assign 50 subjects to the treatment group and 50 subjects to the control group. In this case, we have two independent samples and would use the unpaired form of the t-test. The randomization is not essential here. If we contacted 100 people by phone and obtained each person's age and gender, and then used a two-sample t-test to see whether the mean ages differ by gender, this would also be an independent samples t-test, even though the data are observational. Paired samples. Paired samples t-tests typically consist of a sample of matched pairs of similar units, or one group of units that has been tested twice. A typical example of the repeated measures t-test would be where subjects are tested prior to a treatment, say for high blood pressure, and the same subjects are tested again after treatment with a blood pressure-lowering medication. By comparing the same patient's numbers before and after treatment, we are effectively using each patient as their own control. That way the correct rejection of the null hypothesis can become much more likely, with statistical power increasing simply because the random between patient variation has now been eliminated. Note however that an increase of statistical power comes at a price. More tests are required, each subject having to be tested twice. Because half of the sample now depends on the other half, the paired version of students' t-test has only n/2 or 1 degrees of freedom. Pairs become individual test units, and the sample has to be doubled to achieve the same number of degrees of freedom. A paired samples t-test based on a matched pair sample results from an unpaired sample that is subsequently used to form a paired sample, by using additional variables that were measured along with the variable of interest. The matching is carried out by identifying pairs of values consisting of one observation from each of the two samples, where the pair is similar in terms of other measured variables. This approach is sometimes used in observational studies to reduce or eliminate the effects of confounding factors. Paired samples t-tests are often referred to as dependent samples t-tests. Overlapping samples. An overlapping samples t-test is used when there are paired samples with data missing in one or the other samples. These tests are widely used in commercial survey research and are available in many standard cross-job software packages. Calculations, explicit expressions that can be used to carry out various t-tests are given below. In each case, the formula for a test statistic that either exactly follows or closely approximates a t-distribution under the null hypothesis is given. Also, the appropriate degrees of freedom are given in each case. Each of these statistics can be used to carry out either a one-tailed test or a two-tailed test. Once a t-value is determined, a p-value can be found using a table of values from students' t-distribution. If the calculated p-value is below the threshold chosen for statistical significance, then the null hypothesis is rejected in favor of the alternative hypothesis. One sample t-test, in testing the null hypothesis that the population mean is equal to a specified value I1/4 one uses the statistic. Where is the sample mean? S is the sample standard deviation of the sample and n is the sample size. The degrees of freedom used in this test are null AA1. Although the parent population does not need to be normally distributed, the distribution of the population of sample means is assumed to be normal. By the central limit theorem, if the sampling of the parent population is random, then the sample means will be approximately normal. Slope of a regression line. Suppose one is fitting the model where xi, ia equals a1, an unknown, I plus or minus and I squared are unknown, and I micron I are independent identically normally distributed random errors with expected value 0 and unknown variance I2 florins, and ia equals a1, an are observed. It is desired to test the null hypothesis that the slope I squared is equal to some specified value I squared 0. Let then has a t-distribution with null a2 degrees of freedom if the null hypothesis is true. The standard error of the slope coefficient can be written in terms of the residuals. Let then is given by independent two-sample t-test, equal sample sizes, equal variance. This test is only used when both the two sample sizes are equal. It can be assumed that the two distributions have the same variance. Violations of these assumptions are discussed below. The t-statistic to test whether the means are different can be calculated as follows. Where here is the grand standard deviation, 1 equals group 1, 2 equals group 2. And are the unbiased estimators of the variances of the two samples. The denominator of t is the standard error of the difference between two means. For significance testing, the degrees of freedom for this test is 2 null a2 where n is the number of participants in each group. Unequal sample sizes, equal variance. This test is used only when it can be assumed that the two distributions have the same variance. The t-statistic to test whether the means are different can be calculated as follows. Where note that the formulae above are generalizations of the case where both samples have equal sizes. Is an estimator of the common standard deviation of the two samples. It is defined in this way so that its square is an unbiased estimator of the common variance whether or not the population means are the same. In these formulae, n equals number of participants, 1 equals group 1, 2 equals group 2 null a1 is the number of degrees of freedom for either group, and the total sample size minus 2 is the total number of degrees of freedom, which is used in significance testing. Equal or unequal sample sizes, unequal variances. This test, also known as Welch's t-test, is used only when the two population variances are not assumed to be equal and hence must be estimated separately. The t-statistic to test whether the population means are different is calculated as where here S2 is the unbiased estimator of the variance of the two samples, n equals number of participants in group I equals 1 or 2. Note that in this case is not a pooled variance. For use in significance testing, the distribution of the test statistic is approximated as an ordinary student's t-distribution with the degrees of freedom calculated using. This is known as the Welcher-Satterthwaite equation. The true distribution of the test statistic actually depends on the two unknown population variances. Dependent t-test for paired samples. This test is used when the samples are dependent. That is, when there is only one sample that has been tested twice or when there are two samples that have been matched or paired. This is an example of a paired difference test. For this equation, the differences between all pairs must be calculated. The pairs are either one person's pre-test and post-test scores or between pairs of persons matched into meaningful groups. The average and standard deviation of those differences are used in the equation. The constant I1/4 is non-zero if you want to test whether the average of the difference is significantly different from I1/4. The degree of freedom used is null A1. Worked examples, let A1 denote a set obtained by taking 6 random samples out of a larger set. And let A2 denote a second set obtained similarly. These could be, for example, the weights of screws that were chosen out of a bucket. We will carry out tests of the null hypothesis that the means of the populations from which the two samples were taken are equal. The difference between the two sample means, each denoted by, which appears in the numerator for all the two sample testing approaches discussed above, is. The sample standard deviations for the two samples are approximately 0.05 and 0.11, respectively. For such small samples, a test of equality between the two population variances would not be very powerful. Since the sample sizes are equal, The two forms of the two-sample t-test will perform similarly in this example. Unequal variances. If the approach for unequal variances is followed, the results are and. The test statistic is approximately 1.959. The two-tailed test p-value is approximately 0.091 and the one-tailed p-value is approximately 0.045. Equal variances. If the approach for equal variances is followed, the results are and. Since the sample sizes are equal, the test statistic is again approximately equal to 1.959. Since the degrees of freedom is different from what it is in the unequal variances test, the p-values will differ slightly from what was found above. Here, the two-tailed test p-value is approximately 0.078, and the one-tailed p-value is approximately 0.039. Thus, if there is good reason to believe that the population variances are equal, the results become somewhat more suggestive of a difference in the mean weights for the two populations of screws. Alternatives to the t-test for location problems. The t-test provides an exact test for the equality of the means of two normal populations with unknown, but equal, variances. For moderately large samples and a one-tailed test, the t is relatively robust to moderate violations of the normality assumption. For exactness, the t-test and z-test require normality of the sample means, and the t-test additionally requires that the sample variance follows a scaled I2 distribution, and that the sample mean and sample variance be statistically independent. Normality of the individual data values is not required if these conditions are met. By the central limit theorem, sample means of moderately large samples are often well approximated by a normal distribution even if the data are not normally distributed. For non-normal data, the distribution of the sample variance may deviate substantially from AI2 distribution. However, if the sample size is large, Slutsky's theorem implies that the distribution of the sample variance has little effect on the distribution of the test statistic. If the data are substantially non-normal and the sample size is small, the t-test can give misleading results. See location test for Gaussian scale mixture distributions for some theory related to one particular family of non-normal distributions. When the normality assumption does not hold, a non-parametric alternative to the t-test can often have better statistical power. For example, for two independent samples when the data distributions are asymmetric or the distributions have large tails, then the Weil-Coxon rank sum test can have 3 to 4 times higher power than the t-test. The non-parametric counterpart to the paired samples t-test is the Weil-Coxon signed rank test for paired samples. For a discussion on choosing between the t-test and non-parametric alternatives, see Sawileski. One-way analysis of variance generalizes the two-sample t-test when the data belong to more than two groups. Multivariate testing. A generalization of students' t-statistic, called Hotelling's t-square statistic, allows for the testing of hypotheses on multiple measures within the same sample. For instance, a researcher might submit a number of subjects to a personality test consisting of multiple personality scales. Because measures of this type are usually positively correlated, it is not advisable to conduct separate univariate t-tests to test hypotheses, as these would neglect the covariance among measures and inflate the chance of falsely rejecting at least one hypothesis. In this case, a single multivariate test is preferable for hypothesis testing. Fisher's method for combining multiple tests with alpha reduced for positive correlation among tests is one. Another is Hotelling's TAR2 statistic follows a TAR2 distribution. However, in practice the distribution is rarely used, since tabulated values for TAR2 are hard to find. Usually, TAR2 is converted instead to an F statistic. One-sample TAR2 test. For a one-sample multivariate test, the hypothesis is that the mean vector is equal to a given vector. The test statistic is Hotelling's TAR2. Where n is the sample size, is the vector of column means and is a sample covariance matrix. Two-sample TAR2 test. For a two-sample multivariate test, the hypothesis is that the mean vectors of two samples are equal. The test statistic is Hotelling's two-sample TAR2. Software implementations. Many spreadsheet programs and statistics packages, such as QTiPlot, LibreOffice Calc, Microsoft Excel, SAS, SPSS, Stata, DAP, CTL, R, Python, PSPP, MATLAB and Minitab, include implementations of students' t-test. See also: Conditional change model, F-test, students' t-statistic, Z-test, notes. References: Mahoney, Michael. Sensory Evaluation of Food, Statistical Methods and Procedures. CRC Press. PA 487. ISBN A0-82477337-3 Press, William H. Saul A. Tucholsky, William T. Vettling, Brian P. Flannery. Numerical Recipes in C, The Art of Scientific Computing. Cambridge University Press ppap. 616. ISBN A0-521-43108-5. Further reading: Bono, C. Allen. The Effects of Violations of Assumptions Underlying the T-Test. Psychological Bulletin 57, 49 €64 doi, 10.1037 per hour 00414112 Edgell, Stephen E., and Noon, Sheila M. Effect of Violation of Normality on the T-Test of the Correlation Coefficient. Psychological Bulletin 95, 576 €583 doi, 10.1033/0033-2909.95.3.576 External links: Haswinkel, Michiel, ed., Student Test, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. A conceptual article on the Student's T-Test, Econometrics lecture on YouTube by Mark Thomas.